Hi everyone, in this video we'll see the difference between ArrayList and linked list in Java and when and why we should use each of them. So first thing is both ArrayList and linked list are data structure to store and manipulate a collection of data, and both of them implement the list interface. But there is obviously a bunch of difference between the two of them. So let's start with ArrayList. So ArrayList are a dynamic array that has a default capacity of 10. And the difference between a dynamic array and a normal array that we use typically is that dynamic array expands as you add more element. So when we use normal arrays, we need to define or predefine the size of the array. And once we reach the end, we cannot expand. But with ArrayList and dynamic array, we don't have to predefine the size of the array list, and it will automatically expand when we reach the end. And array lists are good for storing and accessing data, and it's bad for manipulating data, like updating or deleting or adding element in the middle. So as we see here, the lookup or to get data, it's pretty fast. Appending is also fast, but can be a little bit slow in the case of expanding. But assert and delete are slow. So let's go to the source code of ArrayList to understand better. So this is the list interface, right? It extends collection. And if we open the ArrayList class, it implements the list interface as we said. So this is the array that I talked about. This is the dynamic array. It's called element data. And when we try to create a new array list, we either specify the initial capacity, so using this constructor, or if we don't specify the initial capacity, the array list will just create an empty array, this new object array, right? So let's see how get data, so how we can do a lookup and why it is fast. So when we try to get some data, for example, by passing in an index, the reason why this operation is very fast, as you guys see here, lookup is very fast, is because it's just a simple lookup using array. So we just pass in the index and we get the element that we want. So this is the reason why lookups are pretty fast. So let's see adding a new element. So when we try to add a new element, we use this function, public boolean add. We pass in the element that we want to add, and we call this add method that we pass in the element that we want to add, the array, and the size. So let's see how this works. So we have two cases. So the first case is when we are at the limit. So when we are at the end of the array. So for example, let me take this pen. Okay. So if I'm not at the end, so if the size do not equal the length of the array, which means like in this case, I can just append the element pretty fast. So I can just add, for example, 9, and that's it. Like, it's pretty fast. So this is why we have a big O of 1, and we obviously increment the size. But when we are in this case, for example, I have 8 here, I have 1. So when I try to add an element, so when the size equals the element data dot length, here we need to expand our dynamic array. So how we do that? We use this grow method, and we will see now how this grow method actually works. So we pass in the minimum capacity that this expansion need to have, and obviously is this size plus 1. So the minimum we can have is just adding 1 block. So let's see how this works. So what we do is we create a copy of this element data that we have here, but this time we pass in we add a new capacity. So we create a new copy of this array right here, but this one with a new capacity, with a different capacity. So let's see the new capacity that we will add in. So this new capacity depends on the main capacity, right? So right here, let's see. So we do this check if element data equal default capacity empty element data. And this one is, if we go, it's an empty array, right? So let me go back to the grow function, the new capacity function, right? So when this condition is true, we return a new capacity which equals the max of 10 and min capacity. And usually the max of min capacity and 10 is 10, because in this case our min capacity, when we try to add just one element, so let's say we just want to add a new element, just one element, the min capacity that we need to add is 1. But in this case, in ArrayList case, we add 10. And this is why right here I said that dynamic array default capacity is 10. So we usually expand our array by 10, because we don't want to each time expand. Each time I have a new element, I expand. I want to add 10 blocks, so I don't have to each time grow my array. So this is how ArrayList add new elements, and it's pretty fast. It's pretty fast to append new element if we have space, but if we don't, we need to grow our ArrayList, right? But we have some issues with inserting and delete. So let's say I want to insert an element right here in the middle. This operation can be very slow because, as you guys know, in arrays they are next to each other in memory. So at the memory levels, these elements are literally next to each other. So when we try to add a new element or delete an element from the middle, it can be pretty slow. So this is why I said right here, ArrayList are super good for storing. So if I just want to keep adding new data at the end, or I want to look up to this data, I need to use ArrayList. But if I want to manipulate or do some operation on data, it's not recommended to use ArrayList. In this case, we need to use another data structure, which is LinkedList. So LinkedList in Java are a simple doubly linked list, which means we have nodes. So this is the element of the linked list. We call them nodes. And in these nodes, we have the element, right? So the element that contains the data. And we have two pointers, like a pointer to the next element and to the previous element. And the last element of the linked list point to null. Linked lists are good for manipulating data, and the reason for that, let's say I want to add a new element. So I want to add a new element. I can just create a new node right here, and I simply change this pointer. So let me change this pointer right here, and I change the pointer right here, and that's it. It's pretty fast. I don't need to do anything special because these elements are not next to each other in memory. Like this node can be in address like 1, 2, for example. This node can be in address 2, 2. This node can be in address 5, 5, for example. I'm just saying stuff from my mind. And this is why it's easy to add new element or delete new element, because these nodes are not next to each other like array. In array, these elements are literally next to each other in memory. So this is why it's hard to manipulate this data right here. But in the case of linked list, it's pretty easy to do some changes. Also, if you want to delete, let's say I want to delete this node, I simply change the pointer. So I point to this one, and this one point to this one, and that's it. And I no longer have this element. So this is why linked lists are good for manipulating data, but it's bad for accessing data. And the reason why linked lists are bad for accessing data, it's because we don't have an index lookup like we have in array. In array, if I want to access the element in index 2, like I can get it fast, is this one. But in linked list, I need to start from the start pointer and keep searching for this node, because they are not next to each other in memory. So to know where the next node is, I need to see this pointer. So I have to access all these nodes. So for example, if I want this node, I need to start with this one, then the next, and then the next. I don't have the capacity to just go and access the data directly, because I do not know where it is in memory. So this is why linked lists are bad for accessing data. So when we use a linked list is when we want to do a lot of manipulation. And if we go to the code source of the linked list, we can see that we have a size like the array list, and we have these nodes. So let me show you these nodes. There we go. So this is the nodes that I talked about. The nodes right here are created with this class node. We have the item, like the item is in this case 45, for example. We have the next and the previous. So this one point to the next element, and this one point to the previous element. And how, for example, let's see how we add a new element. To add new element, we can we do a test. So if this next, it's null, and this is the case when we are at the end, because the last node point to null. So if this is the case, we just add the node to the last. Otherwise, we add it to before, this link before. And this operation, as I said, is pretty fast. But when we try to get some data, so let me search for this, get some data, we return this node index.item. And this one is pretty slow, and you will see why. Because as I said, we loop. So we have this for loop right here and for loop right here. So when we try to search from data, we cannot access it directly. We need to loop through all the nodes and search for it. So this is why lookup is a big O of n, because we have this for loop, because we need to start from the start and keep searching for the element. So this is basically it for these two data structure in Java. As I said, use ArrayList if you want to store and access data. So you don't want to change, you don't want to delete, to update. And use linked list if you have a lot of manipulation. You have a lot of deleting and deleting and inserting in the middle. So this is it for this video. Thank you.